In this video, we will continue our discussion about loading and processing big data. In particular, we will talk about the encoding of categorical and textual data. So here we go. While working with text data, text is the most widespread form of data. And we see the amount of data generated, many of those data are in text. Perhaps in the company and industry, text is widely produced by all of the data producer in majority of the time. So if you think about text, it can be processed a sequence of character or a sequence of words. And since neural networks do not take input at raw text, we had to figure out a way to convert them to numeric vector, right? So there is a few ways you can vectorize text into numeric vectors. Number one is that you segment text into words and then transform each word into a vector. Number two is you segment text into characters and then transform each character into a vector. And number three, you can extract what's called the n-grams, which is the overlapping groups of multiple consecutive words, and then transform each of them into a vector. Now I show you an example here with different a sentence that you can break into different words, which is follow the first approach. And then from each of the words or tokens here, we can encode them into a separate vector. Right? So here, cat sat on the mat, you can break it into the cat sat on the mat. And then for each of the word, you now have a vector encoding into numeric. And the neural net would take these encoded vector as a representation of the text. Okay, so if you have a smaller number of text maybe, and you can use it at categorical features. So for example, for the California housing data set, the ocean proximity features is a categorical feature. And instead of numeric, it only have a 5 possible value, and it is either 1 hour less than 1 hour from the ocean. In England, it's near the ocean, it's near a bay, or is an island. So you run into this kind of categorical feature sometimes when you look at data, right? And when you have a small number of categorical features, you can potentially use one-hot encoding to encode these text feature into numeric. So if you recall, one-hot vector is a vector where it is co-everywhere and only one hot. So when one element of the vector equal to 1 and the rest of them equal to 0. That's the one-hot vector. So review. So the way we're going to do this encoding is first we're going to map each category into its index. So for this case, since we have 5 categories, the index is from 0 to 4. Right? And we're going to encode that into a lookup table. We also need to add a few more out of vocabulary buckets because we don't know whether we have some noise or some unknown feature or category we need to handle later on. So then we can add a few out of vocabulary buckets, and this usually called OOV buckets. So the code for doing this is very simple in Python. You have your vocabulary would include the 5 features, and you can set up an index here with the range of the vocabulary. So this would give you 0 to 4, and then you create a lookup key value tensor initializer, and this will give you that lookup table. You might establish how many out of vocabulary buckets you like. In this case, we use 2 extra buckets for that, and then you can use static vocabulary table lookup. So what happened here, now you have built a table with these different categories. Now, the more unknown category that you expect during training, maybe you have quite a bit of noise, or maybe you would have some category you didn't encounter before, then you should increase the number of OOV bucket that you have. And then second, we're going to use tf.onehot to convert this lookup index into one-hot vector that the format that we want. So again, you have different categories here. So basically what I'm seeing here is sort of think about this at a test set, right? So I want to see how this kind of category convert into one hot vector based on my table that I looked up earlier. So I could have nearby, desert. Desert is the category that did not in the lookup table, and they have a couple of repeated categories. So when I use a table to look up this category, I may get returned some index in that lookup table, right? So you can see the correspondence here is NumPy array. The nearby would be a map to the fourth or number 3 category. The desert is not included, so it will map to something that in the OOV bucket, which is number 5 in this case. Remember, the index would be from 1 to 6. It's 5 category plus a couple of OOV bucket. And then England is actually the second category, so it mapped to number 1. And then you can use one hot vectors here to map from the category index and using this at a length. So a length would be your vocabulary, in this case 5, and the number of bucket, which is 2. As the result, your one hot vector, we have size of 7, and there is 4 of them because you have 4 category that you want to test here. So the shape that you return, one hot shape, you return is 4 by 7. Each of these are 4 one hot vector of size 7, right? So the first one, the nearby, which is the third category, then you can see 1, 2, 3. The fourth position would be 1, and the rest would be 0. The desert correspond to the fifth positions, which in this case 0, 0, or the fifth index here, and the England will be index 1, which is the second position. I know we all start index at 0, that's why you have a bit of shift here, but you can see these are how we can represent these one hot vectors. Cool. Here I actually have a text vectorization layer that can attract vocabulary from data sample and then do the conversion and the mapping to one hot for you. So it's a very convenient way for you to do it. But if you had to write it yourself, this would be the extent of code that you can write. Now, what is the limitation of one hot encoding? Well, number one is it's pretty good for small vocabulary, but if you have a large vocabulary like this one, have vocabulary of a small English dictionary, right? From A to Z, Aaron to Zulu, and unknown for the outer vocabulary. Maybe you have 10,000. So what happened if for each of these words, you now have a vector of 10,000 to represent it, which is not very sufficient, right? You have a lot of 0, very sparse. But more importantly, the order of the category in these vocabularies do not have any intrinsic meaning. What do I mean by that? So for example, if I have a words here in the dictionary, such as man, woman, king, queen, apple, and oranges, and you notice the index here, basically the index here is just the order of the word appear in the dictionary, right? So you notice that word like man will appear somewhere in the middle, so like 5,391 index out of a 10,000. And woman, because it starts with W, it's appeared toward the end of the dictionary. So when you have a one hot vector, this one hot will be toward the end of the dictionary. King right in the middle, queen a bit on the back. Apple would be sort of in the beginning because it starts with an A, and oranges again somewhere in the middle. So now if you look at this, these two words, for example, man and woman, appear in different part of the vector, so they don't really have any like good relationship. Same with apple and oranges here. Apple at the beginning, orange at the end. And sometimes having this kind of embedding may do not give you any advantage over saying if you know how to fill in the word of this sentence. If it is a blank, I want a glass of orange, and you learn that, okay, the word you should fill in is juice. Great. So every time you see an orange, you want to fill in the word juice, right? So far, so good. But then we couldn't do this. Like we say, we want a glass of apple. Now, because the apple and orange in this extent having different index and they're vastly different, they're not the same here. So it's going to be hard for the machine to fill up the word juice here because there's no semantic relationship between apple and oranges. So a better way to do this is to introduce word embedding, right? So Embedding means that each category will be embedded into a vectorized feature space, right? And so let me give you an example again using the same words at the last example. So you have man, woman, king, queen, apple, and oranges, and they have associated index in the old dictionary or the one hot dictionary, right? Now, if I look at, say, gender, I can now map each of these words into a scale of gender, right? For example, if men here, gender -1 and woman would be 1. So think about it, gender is like in two extreme, men and women. The king would be, similar to men. The king would be mostly male, and the queen would be mostly female. Accounted for some noise when you learn the weight. And then the apple and oranges will be gender neutral. They don't have any gender. The next feature in your embedded vector space could be like loyalty. So in that case, man and woman don't really have any royalty, but queen and king certainly have lots of royalty. So they have high scores here, 93, 95. And then apple and oranges really don't have any royalty. And then age, men and women kind of neutralize when it comes to age. Can't really tell because across the spectrum, but king and queen tend to be maybe older, so maybe here the score will be in the 7s or 69 here. Apple and oranges, not much different, neutralized there. And then food, right? Well, man can be sometimes used as food, like for lion and stuff. I'm just joking. But not really, right? So it's really slow in the score. Same with king and queen. But apple and orange is pretty high on the food because they are type of fruit, which is a food. And then you can have many more of these features. In particular, you can choose, maybe in this case, 256 feature to describe different kind of these in your vocabulary. So in a way, we now represent each category at a 256 dimensional vectors, right? So the nice thing about this is that apple and oranges now appear very similar in this embedded space. If you look at the matrix, the vectors here, right, they are very similar now. They're not all the same, right? So if you have a category features here called colors, maybe then or red color, then apple would be very high on the red, whether oranges are not really. And if you have orange at the orange color, then you have orange score high here, which apple score lower because you don't see an orange apple, are you? Right? So in this kind of embedded space, the object appear to have more relationship to each other. It's have some meaningful here. All right. So how do you visualize this word embedding space? You have 256 dimension. If you want to visualize it, you have to map it down maybe 2 or 3 dimension. And we have this wonderful algorithm to map from a 256 dimensional space or higher space into a 2D space called TISNE, or the T-Distributed Stochastic Neighbor Embedding, a visualization tool by Martin and Hinton. So if you learn this sort of vast word embedding and you map into 2-dimensional space, you still can see some relationship between these words. For example, you can see here the wind, ice, and climate are pretty close to each other. They all talking about the climate, right? Water and seas are similar. Fish, eggs, and meats are kind of close together compared to other words, right? You have heat, electricity, energy, fuel, oil are all clustered very close together here. You have coffee, which is close to drinks. Also drugs, I guess because it's addicted. So they have some further away relationship. You have power, strength, unities are close together and also close with jurisdiction and base and defense in this space. And soil, surface, ground, land kind of close together. So you can see in this space, even though you project down to a real lot lower dimension, the words still have some semantic meanings that you can see they are close together, which is a really nice property. Speaking with property of word embedding, if you learn the right embedding, then the geometric relationship between the word vectors should reflect the actual semantic relationship between these words. For example, if you have synonyms just as accurate and exact, when they map to the embedded space, they should map to be a similar vector. Right? So a nice property about this is that we can use vector arithmetic to map from one category to the others, right? So let's get back to our example here. You have man, woman, king, and queen. So can I do some vector arithmetic here to map from one category to the next? For example, here I might want to map maybe from, how do you go from a king to a queen, right? And, in our semantic mind, we can say, okay, you can just take the king and remove the gender from it and add a woman, a man, and add a woman, then you can maybe close to a queen. That would make sense to us, right? In fact, it also makes sense in the vector arithmetic, right? So you take a king vector and you subtract the man vector, which is this one, right? So you can take, this minus that minus that, so on and so forth, right? So you can see between king and man, you can see the loyalty and the age gonna show the difference, right? And then if you add a woman vector, which is this one, you add this one back in. So you take king minus man plus woman, will get you a vector very close to the queen vector, which is really sweet, right? And not only that, you can do this with other category as well. And I'm gonna give you another example here. A tiger minus a cat plus a dog gonna get you really close to a wolf. And the semantic reason behind this is when you take a tiger and subtract a cat, what you see is you convert from feline to canine when you added a dog here. So you get back a wolf, right? Similarly, if you take a wolf minus a tiger and plus a cat, you are transforming from a wild animal to a pet, so you end up getting a dog, right? So I guess if you learn a really good word embedding, you're going to be amazing at some IQ tests or a SAT, because if you do some analogies, they'll be really good at it, right? But if you learn the right embedding, these now represent not only just the closeness in the embedding space, but also represent some semantic meanings of the words as well. Okay, so what's the difference between word embedding and one-hot vector encoding? You see before that one-hot vector encoding is pretty sparse, high-dimensional, and it's not very sufficient. Word embeddings are lower dimensional, right? Could be from 16 all the way to 512 or 1024 dimension per application, that can be learned from data, and typically they pack more information than the dimension, right? So one hot encoder, if you look at the full vocabulary, you may deal with 10,000, if not 100,000 of dimension, but word embedding is a lot smaller than that. Some of the visualization that you see over here. There is two ways to obtain word embedding. Number one is that you can actually learn them jointly with your main task. So you can learn it with the other network parameter. And number two is you can use some pre-trained embedding so that you can adapt it to your problem. All right. So if you want to say, yes, I want to learn the embedding jointly with the task, how would you do it? You can implement the embedding using a Keras layer embedding that's provided to you. It's actually really convenient. Basically, then you can create a Keras model that can process categorical feature alongside with the numerical one. So you can treat, you can think about this categorical now as just embedding weight matrix that you can learn along with other numerical weights. Right? And, then you learn the same way the categorical feature at your regular features. So you can learn it just using some optimization like gradient descent to learn the weight of the embedded matrix or vectors. So we're going to show you the code that you 2D embedding, but in practice, the good rule of thumb is that you use slightly higher dimension to learn this embedding. Depends on your task or your vocabulary. Right? So this code basically just give you some, representative input, and then you also have a category, and the category will be mostly from the string, right? So text. And then you have a lookup table to look up index, and then you build the embedding layers. Basically, just set you kind of that embedding weight matrix so you can learn. Input dimension is 6 because you have like 6 dimensionality from last example with the California ocean proximity. The output here you specify at 2, but you can do higher dimension if you like to. And then you concatenate the embedded input with the regular input. Then you build your dense layer to learn the weights, right? And then you can specify the model input and output. Again, this is a simple example, but you can see here you can concatenate your embedded weight matrix with the regular input and then learn them together, right? And that's the nice thing about it. Now, I showed the codes here, but in practice, you never really learn this embedding this way, and for a good reason. The reason is that there is pre-trained embedding available for you, and so you can just use those to learn. And it can come from very powerful pre-trained space. And the most famous and successful in word embedding is the scheme word-to-vec algorithms by Thomas Mikolov at Google. And this embedding theme based on a very large corpus from Google News. So it know all the vocabulary and the embedding meaning behind it. Now, if you don't like the word-to-vec, you can use another free train embedding called the Global Vector for Word Representation, or GLOVE, developed by a researcher at Stanford in 2014. And GLOVEs are trained on data obtained in Wikipedia and Common Crawl. So you have choices to loading some free train embedding for your application, and say that if you load this in, so basically what that is, it's just a shoe matrix with the embedding size at the row, right? So these are like, 512, 2014 dimension, and then the column is the number of vocabulary. So you can think about it maybe 10,000, perhaps a lot more, depending on your vocabulary. And then you would having a one-hot vector, depending on the word that you would like to learn, you will have one-hot vector represented. And then you can extract by simply, extract the word embedding and simply do a matrix multiplications here, right, to get you the kind of encoding. So think about it, the word embedding is that you're going to select a columns here in this huge matrix about the word that you're looking for, right? Now, in practice, you don't really do all these matrix multiplication to look up the embedding column. Instead, you use the embedding layers that provided to you by Keras, and that will handle the embedded matrix for you. So really nice, powerful tool. You're going to get a chance to practice them in the tutorial. Now, but I want to talk about a slightly more important topic in the word embeddings is addressing a bias that happened there. And the bias here is not in the context of bias and variance, but really it's a prejudice in favor or against one thing, person, or group, right, compared to another. So unfortunately, word embedding sometimes capture our worst biases. And the famous example is that man to kings again. It can learn man to a king and a woman to a queen. But they unfortunately can also learn that man to a doctor as a woman to a nurse. And that is quite a sexist bias, right? And this bias is reflected along with other gender, ethnicity, age, sexual orientations from the text that is used to train the model. And the texts are written by people, us. So here I show you an example of some extreme gender stereotype. You can read for yourself here, and this also has some analogy for gender stereotypes, such as this is of a she/he analogies here, right? So it's nurse, surgeon, giggle, chuckle, volleyball, football, diva, superstar, softball, baseball. But they also have some gender appropriate she/he analogies, such as queen, king, waitress, waiter, brother, sister, and so on, right? So the question here is, how do you differentiate between the two, whether it's a gender appropriate or gender stereotype? And then how do you make a correction, right? So this is a very important and active research topic, and we're not going to get a lot of time to get into this, but you basically, that you figured out a way to do some neutralization to the words. And this is, I'm going to give you a quick example from a paper from Bulot-Basky and other in 2016. So the idea is to first identify the bias axis, right? So in this case, what they do is they take in the word embedding the difference between he and she, man and woman, or male and females, the difference from the embedding, and they will find this this X exit here, and this is one basically say that the gender should be on one side, like he or female, or he or male should be on one side, while male, females, or women should be on the other side. So that specify that exit. And then they have another exit to denote the gender neutrality of the word. So you can see here in this embedding, the word that below here are neutral to the gender stereotype, but the word up here are not. Right? This word up here is the stereotyping. So what you can do here, two things. You can do neutralization to the words here. So what you can do is anything that above this axes are considered biased word, and you can neutralize them by collapse all of these words into this exit. Right? This exit is supposed to be neutral. So you want to move all these words using vector arithmetic to move all this vector, collapse them into this exit. Right? So they no longer lean toward the male or female. Right? Now, hopefully you can get rid of some of the bias that way. And then another one at the same time you have to do this is that you have to also equalize. So some of these words appear in the dimensional embedding space are not equidistant to the bias axis. So what you do is that you have to also correct them so they will be having equidistant to the axis. So words like mommy versus daddy, right? So mommy is here and daddy is here. So what you do is that you had to move mommy maybe to here, daddy to here, so that they have the equidistant to this exit, right? And you can do this the same for other appropriate gender, such as daughter and son, sister and brothers, sorority and fraternity, so on and so forth. So any words that appear down here in your embedded space, you want to also move them so that they have equidistant to the bias exit. Right. So I know it's not a lot of details on it, but you certainly can read the paper link below. You learn more about detail. I just want to simply introduce you to the concept of neutralizations there. So in summary, when you work with categorical or textual data, you can try to train the embedding yourself, but you're probably better off using a pre-trained embedding instead. And, this module, you learn a lot about data API, TF record, TF data set, word embedding. So all of these tools are going to be very important for you to build a highly scalable pipeline. And you also benefit from a fast and portable data pre-processing in production of your deep learning model. And just want to know that ensuring fairness in machine learning is an important topic that we hopefully would explore either throughout the project or later on in the course. So with that, we close this video, and I'll see you in the next video.